again the
Yes,
recording.
yeah,
Okay.
you can record.
Nelly, can you do it?
Yes.
Okay, so let's take this example for mutagenicity, and we use the consensus model plus the 4 individual models. And what you have is a kind of summary. So this is the substance of interest. This is predicted mutagenic with a consensus of 0.15 based on 4 models. And you see there is a mutagenicity score 0.15, non-mutagenicity 0.15. So it is exactly the same. What is the meaning of this? In the what we call the consensus model basically integrates the results of 4 other models. We have one model, Caesar, ESS, SARPI, KNN, stating something we will analyze. And so we have one point which is the prediction, mutagenic or not, in case of conflicting value, same score. This is assigned for the more toxic part of the two. And this score goes from 0 to 1. 0 means I'm it's very uncertain. 1, I'm very, very sure. And there is one measurement for the mutagenicity from 0 and 1, and another measurement for non-mutagenicity from 0 to 1. And so here I'm very close to uncertainty in both cases, because I have 3 models stating non-mutagenic and one model stating mutagenic. So this also depends. There are different ways to integrate in some software. Simply make the majority vote. In this case, the result would be non-mutagenic, 3 versus 1. There are other ways to integrate the results which prefer to say, okay, I have 3 models with low reliability. I have 1 model with moderate reliability. I disregard this and I prefer this. There are, in the paper that I mentioned, which is freely downloadable and available, all these different procedures are described and commented. Here, again, we show all the results. The way to integrate it takes, done as in done within VEGA, it takes into account the value of the ultimate it is mutagenic or not, and the applicability domain index, which is a quantitative value. And in this case, by chance, it is resulted to be the same. So how to do? We have to evaluate each line of evidence. So we have this kind of, the first model is Caesar here. And it says it is non-mutagenic, reliability is poor, because for the accuracy, for the similarity. This is what is said. The accuracy is not so good. The concordance is not good. Indeed, so I have to look particular attention to these 2 points. I have a similar comparison. This is very similar. 0.969 is very close to 1, which experimentally is toxic, but it is predicted non-toxic. That's why I have the poor accuracy. But also the model predicts non-toxic, while here I have something which based on the experiment is indicated toxic. And also the concordance is very critical. And then there is another similar compound, well, not so same, 0.82, which is non-toxic and again predicted non-toxic. I have another one. This one is mutagenic, but it's predicted mutagenic, but it contains something else. So to me, this is partially of interest. This is not of interest. Definitely, this is the same. If you remember the target compound, the difference is 1 carbon. So here, only considering this model, the Caesar model, I have this target compound, which is predicted non-toxic. So I have one line of evidence, which is the prediction. But I have another line of evidence, which is the read across, which is very strongly pointing toward toxicity. So to me, it will be very, very difficult to overrule this very strong line of evidence. So I have from the Caesar model. The Caesar model says non-toxic. This is what the Caesar, but out of what is shown here from Caesar, my assessment from the Caesar model is that this target compound very, very, very probably will be mutagenic, not for the prediction, but for read across. So I disregard the prediction and I take into consideration this. Of course, there are differences, 1 carbon. Of course, I know that there are, I don't know, aldehydes. The short aldehydes, they are mutagenic. If you increase the chain, so if carbon 1, 2, 3, maybe 4, they are mutagenic, 5, 6, they are not mutagenic. Something similar also happens for chloroalkanes. The short isomers, 1, 2, they are mutagenic, probably 4 is not mutagenic, if I well remember, you can check. So surely there is a difference. And surely if you increase this chain, this may at a certain point arrive to a different kind of effect. But based on this element, I cannot demonstrate that the target compound is non-toxic. So based on read across, I have only one chemical, unfortunately, and my evaluation, honestly, would be that no, Caesar is wrong. This I can trust on this. This chemical is not so interesting to me. It's a different story. I don't have this particular. This is not accounted as a different structure, but basically these two structures are very different indeed. Also, you can see this value is very much lower compared to this. So based on Caesar, I can arrive to this conclusion. From SARPI, basically I arrive to the same conclusion. I have a structure alert for non-mutagenicity here, and I can quickly go and simply the model says that quite frequently these kind of chemicals are non-mutagenic, but here I have a different story. I have a very different evidence, and so I disregard the reliability in this case of this fragment is quite is lower. This is a model, the Benigni-Bossa model from Istituto Superiore di Sanitas in TOX3, again stating non-mutagenic. I have a different training set. So I have different similar chemicals, not so similar, so not so important, and I do not have rules. So for the Benigni-Bossa, here there's no concern. And here, here you see that this is what I mentioned. There is one rare fragment. Yeah, you see atom center fragment. So in this case, as I said, the Benigni boss has a lower training. The training set is about 1,000 chemicals. And so within the training set of this model, this appeared as an unusual fragment. There were only 3 chemicals. So this is what referred to the previous question. But again, this indicates, but there's no particular structural alert indicating toxicity. And then there is another model with a higher reliability, which is non-parametric, is simply looking at the most similar compounds. And here again, I have this chemical, which is toxic, this, which is non-toxic, something similar we have already seen. And so overall, 2 out of 3 are toxic, and simply the model says, okay, it's toxic. But again, this is, yeah, maybe this is part of the story, but I'm not sure, because here we have seen from the other model that this may be toxic for other reasons. So this is not relevant. This, in my case also, is not relevant. All the evaluation is done, unfortunately, only on this. But this is very strong similarity, and so I somehow take advantage of this model simply to have a number of lines of evidence, but then it's up to me to identify the really strong line of evidence. I have another example here, which refer to this substance. This is the opposite, indicated mutagenic, consensus 0.25, but non-mutagenic 0.22.2, and here is 3 models indicating mutagenicity, 1 indicating non-mutagenicity. So very, very similar situation. This is Caesar stating, oh, this to me may be toxic. I have no structural alert. So this is based on the statistical model. Basically, this is the summary. Very poor applicability domain, accuracy, strong issue, concordance terrible. This is predicted toxic, but I have a very similar compound which is non-mutagenic. It is predicted toxic. Okay. This is another similar compound, non-mutagenic. So here I have the amino, the pheno, the carboxy. And they are non-mutagenic. You may say, okay, but here I have amino in a different position. For instance, the amino is in a para compared to the carboxy, while here the amino is in meta. So maybe the amino in para means toxicity. You may have this question. No, the answer is not. Even in case of the amino in para, the chemical experimental is non-toxic. So you may wonder, okay, what about if I add an hydroxy? The hydroxy basically increases the hydrosolubility, so it reduces the toxic effect. This is also documented here. So based, in this case, I have more evidence. Based on 3 chemicals, 1, 2, 3, I know that these components of the amino, which in many cases is accounted for issue, basically, again, the all the elements point in all the experimental value of the read across points in the opposite direction. We may consider the other models, and we can get to the same conclusion because these are the same. For instance, this is the Benigni boss. I said, oh no, I have a mean aromatic amine, but there are exception rules indicating that this actually is predicted non-mutagenic if it is in ortho. Actually, this applies also when it is in para, and probably this is not accounted by the Benigni boss. So this is one of example. Maybe very quickly, just to show tox read. I'm running now the tox read for substance, and I get this kind of predictions. The substance is this one. If you click here, you get all the results from the VEGA models indicating lack of toxicity and all the assessment from the similar compounds. And basically what you can do here in this case is to evaluate, there are no structural for toxicity. Consider the most similar compounds which are toxic and see if this may represent a problem. The structural alerts, we have structural alerts for lack of toxicity, which basically are this ring, this case, this ring, and the bromobenzene. By the way, structural alert 1, 2, and 3 are not present in any of the model from Caesar. These are present only in tox read. In VEGA, you only have this structural alert, which is broader. It simply say, okay, that this fragment may be associated to mutagenicity. Indeed, there is one example here, but the three most similar compounds, they are very similar. Here I have a chlorine instead of bromine. Here I have the pyridine. But we have already seen that this moiety means non-toxicity. It was this fragment. We have already seen that the bromobenzene means lack of toxicity. So I can, because I may wonder, oh, but there are differences. No, they are no concern. And then I can have a look at if I want to do this more similar compound. But here I will see that these are similar, but not so much, and the toxicity is associated to the fact that they do contain the nitro group. So they are very different compared to this. So this is basically how to little bit play also with the tox read. We can finish with slides and the examples if there are questions.